In the last part of this module note, we're going to be looking at building histograms and how histograms vary from bar graphs. So the first thing we should know about histograms versus bar graphs are that histograms are used for continuous quantitative data, and so we can think about the x-axis just like a number line, okay? And this is a little bit different, right, for bar graphs. Bar graphs are used for categorical data. So this example that we're going through here, we're using BMI data because, as we discussed when we're categorizing data to begin with at this unit, BMIs can be thought of as categorical, underweight, normal weight, overweight, obese, or they can be thought about as quantitative as far as measurement goes. Okay, and so the same information can get portrayed in two different ways. So some of the big differences are bar graphs. We see space between the different categories, and you're going to be building bar graphs in Excel as part of an activity. And then with histograms, again, because of the continuous nature, there's no space between the bars, okay? In both graphs, we see the frequencies up the vertical axis or the counts within each of the categories. So let's look again at how we might build histograms and some more terminology around it. So to begin building our histogram, we need to first create our frequency table. Okay, our frequency table is built from raw data, which is information that we'd be collecting from members at large. So for this particular graph, we've got raw data from 20 individuals, and we've got it divided between male and female. Okay, so we see in the first class of BMI from 15 to 19, 7 male. And that comes just from, if we go through that raw data, and we find how many numbers are between 15 and 19, there's 7. If we did the same thing with the female data, right, and looked at how many BMIs were between 15 and 19, we'd find 8 pieces of data. So we can go through and do that for all the data, figure out the counts. Our totals should add up to the total number of people represented. And the relative frequency is given by the number in the category over the total amount. And it's expressed as a decimal, and we'll represent it to 4 decimal places. We'll start getting into that habit because that technique's going to come up again in Unit 3, where we're going to be representing values out of 1, and we're going to be representing them as decimals to 4 decimal places. So as we start building our histogram, some terminology we're going to talk about. We're going to be talking about finding our class intervals or our bins for our classes. And the class intervals, the bins, the classes, those are those intervals like 15 to 19 or 20 to 24 that we're grouping our raw data into, okay? It's important that our classes are non-overlapping, okay? What doesn't appear in those groups are the class boundaries. So because our classes are non-overlapping and we can only put one label on our x-axis, you'll note, okay? The value that we use to label our axes is what we call the class boundary, or the real boundary. So our first category goes from 15 to 19. Our next one goes from 20 to 24. But because the values are continuous numerical value, they were rounded. And so that category from 15 to 19 has a real upper limit of 19.5. Anything that's 19.5 or lower would round down to 19. Anything that's 19.5 or higher rounds up to 20. And so that real limit is what we're going to label on our x-axis. And again, it's just the midpoint. It's the average between the upper limit of one category and the lower limit of the next successive category. Okay. Another word expression that we should be familiar with is class width. So the class width tells us how wide each of the classes are. It is not the difference between the upper limit and the lower limit for a class, but it's a difference between the successive lower limits. So if we think that 20 minus 15 is 5, each of our classes represented here are actually of width 5. How many classes we're going to use to group our data and how wide the classes are is a decision we make early on in the graphing decision, in the graphing process, and there's equations that will help us that we'll look at shortly. The difference between the number of classes that we use changes the look of the graph. We could organize the same data with different width classes, and the result is that the graph gets smoother or more or less pixelated or more or less smooth depending on the number of classes that we use. So the next thing we're going to do before we begin creating our frequency distribution tables is just go over those equations that can help us along the way. So general rule for classes is typically we want between 5 and 15 intervals. Okay, we talked about this before. The limits have to be non-overlapping, so we need the data can clearly only go in one interval. All of the classes need to accommodate all the raw data, so the minimum should lie within the lowest interval and the highest in the greatest one. Or it might be possible that we have a class that has nothing in it, as actually we'll see in our first example. Okay, and then the other piece is that intervals need to be of the same width. So once we decide how wide our intervals are going to be, they all have that same width. Okay, again, between 5 and 15 intervals, more data, more classes. So how do we determine how many classes we should have? There's a formula for it. So there's Sturges Rule, and it says that K, the number of classes, should be at least as large as 1 plus log base 2 of the number of data values that we have. So let's say I have n equals 200, right? Then I'd have K should be greater than or equal to 1 plus log base 2 of 200. Okay, putting that into our calculator, we'll remember that log base 2 of 200 we calculate as log of 200 divided by log base 2. And so that comes out to 8.64. So that means that ideally we should use at least 9 classes if we have 200 pieces of raw data. That might not always be the case, right? With the BMI data that we just looked at, if there's other categories that would affect that decision, we might not always use 9 classes, but that's what the rule tells us. So you'll see a link in the notes that takes you to a website that talks about how binning works and what happens when we have too few bins, too many bins, and some of the other things that we'll talk about. It also introduces several different formulas for calculating bin numbers. We're going to use Sturges Rule, but there are other formulas you can use to calculate the number of bins required for a particular data set. Okay. Once we know approximately how many bins we're going to make, then we can figure out how wide they should be by figuring out the range of our data, the difference between the maximum and the minimum of our data set, and dividing by the number of values we have. Again, As far as class interval widths goes, we're generally going to round to friendly numbers. So we're going to want classes that are maybe 5s or 10s or 15s or so on, so that it's easy to count. Okay, with that information in hand, let's go on to building our first frequency table. For this first one, we're not going to use the formulas. We're just going to do as we're told. So we've got some raw data given here, and we're asked to develop the frequency distribution table using class intervals of width 50 and a lower class limit of 1200. So that means that our lower limit for our first class is going to be 1200. Because we know we're going to have classes of width 50, then our next lower limit is going to be 1250. Okay? Because our classes are non-overlapping, that means our upper limit for our first class is 1249. Okay? Our classes are all equal width, so it's actually easy to figure out what all of the lower limits are first by adding 50 to each successive class, and then we can go back and we can figure out what the lower limits need to be. Okay, so that's a good technique to use to make sure that we don't accidentally make classes that are either overlapping or accidentally of different widths. Okay, once we have our class limit set up, we can go about tallying our values. Remember to tally, we figure out our value and then we put a tally mark in whichever category it belongs to. I find it easy to go down columns and to cross out as I go to make sure that if I get interrupted, I remember where I was and continue on as so. So what I'm going to do now, I'm going to pause the video. I'm going to leave it to you to tally up, count the frequencies, and to calculate the relative frequencies. Okay, you can check your answers afterwards. As far as the real boundaries go, I'll remind you about that. So the real boundary is the midpoint between the upper limit in one category and the lower limit in the next category. So we'd have the following values for the first few categories. And again, you'll notice the distance between the real boundaries is equal to the class width as well. So that's a good thing to keep in mind too. So again, pause the video, finish filling out the chart, and then check back with the notes in a second. Okay, your frequency distribution table should look as follows. If you have any questions, don't hesitate to contact your instructor. Let's go on and look at the next example. So in this situation, we now have data for 60 patients, and we're asked to create a frequency distribution using the raw data. We're not told how many classes we should use or how wide they should be, so we have to use our formulas. So remember, to figure out the number of cases k should be greater than or equal to 1 plus log base 2 of our n value, the number of values we have. So in this case, it's greater than or equal to 1 plus log base 2 of 60. Plug that into your calculator and see what value you get. It comes out to about 6.9. So this means that it's suggested to use at least 7 classes. Next thing is determine the class width. The formula for class width is max minus minimum divided by k. You need to search through the raw data, find the maximum value, find the minimum value, plug into the formula, and divide by 7. The maximum is 500, the minimum is 420, it comes out to 11.4. Now, we round this value to a friendly number. So we could either use a width of 10, or we could use a width of 15. The choice is up to you at the end of the day. However, I'm going to be using a width of 15, or suggesting that you use a width of 15 because it'll fit in our table properly. Okay, so pause the video now, use a lower limit of 420 at the minimum value, and build your table. Great work. If you have any questions, don't hesitate to email your instructor or attend their office hours. One more short video just introducing the concept of skewness will follow.